Bismillahirrahmanirrahim. Right. So what we're going to do today is start exploring the details of how networks are configured, how we can have devices communicating with each other. So last time we did like a brief introduction to what kind of things there are, and then we moved on to a practical in which you connected the devices together, right? So the whole point of this practical initially, without even understanding it fully, was that now you have seen that different devices can connect to each other using wires, right? You've actually like kind of seen those wires, uh, and you've seen that there are configurations required to make things work even after you've done all the wiring. So it's not sufficient that you have all the connectivity established. You also need to have the support of the software to make things work, right? There was remember that there was a problem with the name. The computer did not have a name, and because of that it was not able to communicate, right? You remember that problem, right? So we are going to explore this further on in this week, and we are going to take a look at how these different communications take place. What are the rules and what are called the protocols? So protocol is essentially the set of rules which are going to help us establish connectivity. There are going to be several protocols. There are going to be several different small pieces. So we are going to look at them throughout this semester, right? So the whole course is going to be essentially talking about different protocols, right? So what are the rules? And you may think that there will be like 2 or 3 rules, right? And then we should be able to establish connection. I mean, I'm sending you data, you're receiving the data, it should be fine, right? But you will see that because we have to make everything work with everything, remember that the whole internet is like everything connected to everything. And now you have to make everything work with everything. So you need to have rules which can take care of all the different use cases, right? So we are going to talk about this today. So again, as before, we are going to do this lesson, inshallah, with slides, and we are going to look at some mosquitoes. We are going to look at some stuff which is going to be theoretical in nature, but remember, it does look boring. I know that it looks boring, right? The numbers are going to be like the numbers themselves are going to be very boring. They're not very interesting numbers. There are some numbers which I think are interesting and some numbers which are boring. So these are going to look like boring numbers, but they're essential. You have to understand them and you have to understand the rules if you're going to make networks work, right? So again, essential. And inshallah, next time we are going to look at something very related to this in a practical, again into the packet tracer, and then it's going to make sense. So I said this before, I'll say this again and again throughout the semester, that the theory is going to look boring, but if you do go to the practical without the theory, the practical will not make sense. So the theory is going to be like somewhat understandable, and then you go to the practical, and half of the practical is going to help you understand this theory, and the other half of the practical is going to help you understand the next theory, right? So every practical that we do is going to be kind of like, yes, I kind of get it, but why, like not 100%, right? All the practicals are going to be like this, but they are there so that when we're doing theory, we can refer back to them, okay? So we are going to start with module 3. There is no module 2 because in these slides, module 2 is completely out of place. It's supposed to be, I think, like module 12 or something, and it's at 2, so we're skipping that, right? So this is supposed to be 3. All right, so let's see. So we are going to first talk about the rules, and as last time we discussed that whenever you want to establish communication, you need to have some rules, right? That is the basic premise. So in communications, you can have different size and complexity, and it's not enough to have a connection. So a connection, a wired connection or a wireless connection, is not always sufficient. You need to have some sort of an understanding between the devices in terms of software and configuration of different elements, right? So you have to be there. And there are basically 3 elements. One is the source, who is the sender. One is the destination, who is sending, and one is the channel, which is the medium, right? So the source and the sender and whatever is in the medium. These are the basic 3 actors over here. And we are going to refer to these 3 things repeatedly. So sender and receiver a lot, and media is going to be kind of like secondary for us. We are going to be essentially dealing with sender and receiver, and media is going to kind of like just be there. It's going to establish connection for us, right? So there is a whole chapter on media itself. We're going to kind of skip over that because we're not coming from the IT side, and from the software side, we're not too concerned with the media. Yes, we need to understand it a little bit, but not that much, right? So we are going to deal mostly with the senders and receivers. Okay. So what is a communication protocol? A communication protocol is a set of rules. That's the basic definition that you understand. It's a set of rules which allows you to establish some sort of communication, right? And as we'll see, even if I just want to send one bit of information from one PC to another PC, I need to have quite a few different protocols, right? And there are reasons for that. We'll come to that. So all communications are governed by protocols. So these are the rules. Remember, the word protocol is very important in computer science, and it essentially means what are the rules, right? Typically for communication, a protocol is typically for communication, right? So the rules regarding communication, that is what a protocol is essentially, right? We don't have a proper formal definition here. So protocols are the rules that communications will follow. If you don't follow the rules, then the other party may not be able to even understand what's going on, right? So we'll see why that is in this just a minute. These rules will vary depending on the protocol. So if you have different types of protocol which aim to achieve different things, then you are going to have different rules. I'll give you a basic example here. We have further examples in the slides in the future. So for example, if your protocol is there in your whole networks to ensure security, so that nobody else can steal data from you, right? It's going to have different objectives. This protocol is just there for security. It doesn't care about whether the information reaches the other end or not, right? This protocol is just for security. So it's going to have different rules, right? As we can imagine. There might be a completely different protocol which tells you how to get your information from point A to point B and make sure that no information has been lost, right? So it's trying to ensure reliability. So this is going to have different set of rules. And as you can see, both of these things are necessary for us. We need security and we need reliability. So we're going to use both of these protocols at the same time. You understand? Okay, so we'll see an example of this later on. So essentially, whenever you are trying to send some information, we are going to call this piece of information a message. Okay, so it's going to be a message which is being sent from point A to point B. Right, device A to device B. Devices can be anything, as you've seen earlier on as well. They can be end devices. They can be intermediate devices as well. They can be server, client, P2P, all of those things. Okay. So this device over here is called the message source or the sender. This is the person who is sending the message to the other party. Okay. The transmitter is essentially going to be the device within your larger device. So you have your PC and inside you have a NIC, for example, right? So network interface card or wireless card, which is supposed to take the message and somehow put it on the medium, right? So this is called the transmitter, which is supposed to take the message and put it on the network media. Okay. So this thing goes over to your transmitter medium, and then there is going to be a corresponding device at the end, which is going to take this from the medium and somehow convert it into a software, and then it is going to be received by the destination, which is your receiver over here, right? So as you can imagine, this is the basic stuff. Okay. So in Packet Tracer, we are going to come to this in the next lab, inshallah. But this thing is this little packet. So it's a little envelope, a little packet, which is used to demonstrate the message. Okay. So whenever your information is flowing on the wire, we call them packets, right? So little packets of information.
This one is encrypted?
They can be encrypted, they can not be encrypted, depends on what you're trying to achieve. Sometimes they are, most of the times they are encrypted, right? And nowadays it's recommended that you encrypt everything, but not everything is encrypted. Sometimes they're not. And when we do security subjects, we actually deal with different aspects of that. So yes, you're right. Ideally, everything should be encrypted, but not everything is. Okay. But all of these are called packets, and that is why the name of the simulator is Packet Tracer, because it traces or follows the packets which are flowing on your network, right? So that is why it's called a Packet Tracer. And in network, we are going to repeatedly call things packets, even when they are not actually packets, right? So what is a packet? It's essentially a piece of information which is flowing from point A to point B. There is a technical definition which is in the slides later on. Okay. So your little envelope is going to be your packet in your Packet Tracer. Okay. So protocols must account for different requirements, right? So we have a few over here. You need to have an identified sender and receiver. If there is some bit of information coming in and it does not have a sender, then protocols simply cannot work, right? You cannot just, as humans, we can stand here and we might be hearing some sort of information, right? We may not know where it is coming from, but it is going to have a sender, right? It can be a device, it can be a human, it can be anything, but there has to be a sender from which the information has initiated. Okay. You also need a receiver, obviously, because if you are sending some piece of information, you cannot send it out to, let's say, I want to use the right words, because if I say something wrong, then the next few slides are going to be confusing. So you cannot send a message out and not put a sender in it, right? If you take like a normal post email, you take an envelope and you put it in the letterbox. You can put it there. The post people will open it up, the real snail mail thing. They will open it up and they will say no sender, so they'll just throw it away, right? So it doesn't work if you don't have a sender. You need to have some sort of a sender. You don't need to have a specific sender. You understand the difference? Right. So I don't have to say send it to this person or this device. I can say send it to everybody. Right? I can say that, send it to everybody. But then everybody is a receiver. I cannot just be quiet about the receiver. If I don't want to send it to a particular device, I want it to send it to everybody, I can say send it to everybody or send it to these 10 people. So it doesn't have to be one specific receiver, but a receiver has to be there. Or more than one receivers have to be there. Okay? All right. We'll see. Again, all of this, as you go forward in networks, the concepts at the back are going to start making sense. Right? And that is, I think I told you the problem with the CISCO Networks Basics course. The problem with that is they assume quite a lot of stuff and most of it does not make sense until you've seen like chapter 5 or something. Okay? Right. You need to have a common language and grammar. So these words are not exactly right. Let's call them rules. Okay? We'll see what these rules are later on. You need to have also an understanding of speed and timing of delivery. Right? So why is this important? I mean, I'm sending a message. It's eventually going to get there. Why is it important to have an understanding of the speed and delivery timing over here? So again, this is probably like a complete chapter on itself, but I'll give you a brief reason for this right now. Why is it important to have an understanding of speed? So if I am sending you some pieces of information, remember how is the information actually flowing on the wire? I'm going to call it the wire. It can be wireless as well, right? So on the wire, it's just electric pulses or optic pulses, right? It's 0 or 1, right? It's a high voltage or a low voltage, 0, 1, right? So let's say you have 1, 1, 1, 1, okay? And then you have a 0, 0, 0, 0. So it's a high and a low, okay? How do you know if it's a 1 high and 1 low or 4 highs and 4 lows? Understand? 1, 1, 1, 1, 0, 0, 0, 0 looks like this. Because what message are you trying to send? Are you trying to send the message 0, 1? Or are you trying to send the message 0, 0, 0, 0, 1, 1, 1, 1? These are two completely different numbers, right? You need to have an understanding of what speed the messages are coming in. If you don't know, then it's just an electric pulse and it looks like this. Do you understand this? High voltage, low voltage, right? So high voltage, low voltage. How many bits of high voltage? If we don't know the speed at which information is being transmitted, we don't know whether these are 4 bits or 15 bits or 2 bits or 1 bit or 1000 bits. We don't know, right? So you need to have an understanding of this low level detail. The good thing is we have created an architecture which we'll start seeing in this thing. When we are working with software, right, we don't have to worry about this stuff. There is going to be a completely different protocol which is going to take care of this portion and we can simply ignore it. Right? This is going to be an important point. We are going to break down this whole as you can see, there are very minor things, very small things which can like mess up your whole communication and you wouldn't even know to think about this. Right? This issue that I just told you, if we had not discussed in class, you may not have thought of it. I did not think of it myself. Right? I studied it from somewhere. So these are very small things which can go wrong in a network, which is on all the time and all the time communicating, right? All of these things can go wrong. So we need some mechanism through which all this complexity, we can somehow manage it and try to learn one thing at a time. You understand? If you try to learn all the issues at the same time, they're not going to make sense. So we need to somehow structure them Just as in an undergraduate program, if I tell you that you're going to come in here and for 4 years we are going to learn computer science, right? So it's going to be very difficult. What do you mean learn computer science? There are many different things, 40 or 50 different subjects just to get started, right? What are we going to learn? If one day we come and teach you one thing and another day we come and teach you another thing, it's going to be very difficult. So we put things in little boxes and try to understand one box at a time. So right now we are understanding the networks box. So in this communication, we are going to break things down into different boxes. Try to, for example, understand security at one point, reliability at another point, how to establish connection from point A to point B another time. Okay. So we are going to come to this. You might also have a confirmation or acknowledgement requirements. What that means is if I send you a message, you have to tell me whether you got the message or not. Otherwise, I just keep sending you messages and maybe the system is off, or maybe an intermediate device is not functioning properly. You're not getting my messages. How do I know whether you received my message or not? Understand? Sometimes this requirement is there, sometimes it is not. It depends. We'll come back to this later on again as well. Right? So do you understand that rules have to take care of all of these different things? Again, we are going to come back to this when we do specific concepts. And there are like 3 or 4 different aspects of communication that you have to understand. And the very first thing is message encoding. For example, you have a message. I'm going to send the message hello world to the other computer, right? Other device. So let's get rid of the whole hello world and let's just look at H. Okay. So I have to send the H, okay, to this other device. Agreed, everybody? Okay. I have to send the device this message H, just H. But H is a letter. We cannot have a letter on the wire. The wire can only carry zeros and ones. So somehow we have to turn the H into first zeros and ones. Okay? Agreed?
Yes.
Right? So how do you turn an H into a 0, 1?
Binary.
You can convert it into its binary ASCII values. Right? So let's say H is, what is H? H is like, I don't know, 75 or something. I don't know. I don't remember the code. But let's say H is 75. Okay? So you take this 75, you convert it into binary, and now you have this thing. But remember, we have to also specify the receiver. So we take this 75 and we somehow attach like the receiver's name to it. Right? And then we also have to attach the sender. We have to prepare this whole thing, the whole communication thing. So when we have this, we may also want to encrypt it. Like you said, we want to secure it. So we encrypt it. But if we encrypt it, have you taken cryptography?
Yes.
It doesn't matter if you haven't, but you basically understand that if you encrypt something, if you secure something, you need to like secure it using some sort of a mechanism. And there are many mechanisms in the world. So now when you encrypt it, you also have to specify which mechanism you used. Right? So as you can see, just that 75 has turned into a big thing and it has a lot of structure into it. Right? You've taken data structures and programming, right? You create a structure or a class to have different fields. So now in this, we have a lot of fields. The H is like way over there in the middle. And then you have the sender and the receiver. And the H is like this big, and sender and receiver. And then you have the whole thing encrypted. And there is an information about how we encrypted this so that the other person can decrypt it. Right? And then there are many other things associated with it as well, as we'll see in the future slides. So as you can see, this whole thing has a proper structure to it. This structure is called encoding. Okay? So we need to have a message encoding. Encoding is the process of converting information into another acceptable form for transmission. Right? So you have to encode it so that it can be transmitted, but not just transmitted in a way that it can be again decoded at the other end properly. Because if you encrypt it and you don't write which encryption algorithm was used, then the other party cannot decrypt it even if they have the key to decrypt it. Even if they are the intended audience, they cannot decrypt it because you didn't tell them which algorithm you used. And you have to tell them which algorithm you used because you just started talking to them. Okay? Is this clear? So you have to specify all of these details when you are trying to communicate. Okay? Alright. At the other end, decoding reverses this process to interpret the actual information. So what is that the receiver going to do? They get the information and first they are going to look at our algorithm. We already have the key shared with each other, right? So they are going to decrypt this whole thing, right? So what do you mean by decrypt? So they basically open up the hidden message using whatever algorithm is there that you specified. Then they open it up and they look at the receiver. they look at the sender, the person so and so sent me this information. And what is the information? Then you get rid of everything and then they say that yes, there is an H there. They actually see a 75, right? And you have to specify that I used ASCII because there are other encoding schemes as well. So you have the H and then you have ASCII written next to it so that they can look at the 75 and decide that yes, this is a ASCII 75 so that it can be converted into an H. Why? Because let's say you were sending not an H but a ha, right? If you were sending that, it cannot be encoded in ASCII. So you would say I'm using UTF-8. Let's say in UTF-8 the ha is, let's say, 5072, right? You understand? So you have to have all of this information for the other party to understand what you're trying to say to them. Is this clear? So this whole thing is called encoding and decoding. Essentially putting it in a form that can be transmitted, and at the end taking the transmitted bits 010101 and somehow opening up all the packages so that you get the original message. So the original message is going to be like this big, right? We're actually going to see what the size is later on when we do practical, but it's a very, very small piece of information and there is a lot of stuff around it. Have you ordered like a very small bracelet online from a very reputable website? So if you like order a very small like earring or bracelet or watch or something very small, and they pack it first in like bubble wrap and then another, and then they put something else around it, and then they put it in a big box and put that box in so that the thing doesn't break, right? So you keep opening and at the end you get like something this small, right? That is essentially what we're doing over here. So encode, and when you receive the package, you decode. Is clear? Okay. So okay, right. So when you're encoding, you need to specify the formatting and encapsulation. So again, when the message is sent, it must use a specific format or structure. Right? What this exact format is, some of it we're concerned with, some of it we're not. We're going to take a look at this thing over here later on. But you can, this is exactly the same thing that I just told you. That in an envelope, you write the whole thing and then you put it in an envelope and you put the sender and the receiver and the stamps and everything on it. Similarly, when you are sending some information on a network, your actual information might be like somewhere over here, right? So where is the payload? So I don't know, somewhere over here, right? So somewhere over here, the very small piece of information, and then you have other boxes around it specifying what you want to transmit, how you have encrypted it, how you are sending it, who is the sender, who is the receiver, what algorithms are used for different purposes, and all of that stuff is around it. And this whole thing then turns into one packet and then you send the packet. Okay, so you need to have all the formatting and encapsulation. Do you know what encapsulation is? So encapsulation is basically taking some piece of information and putting it inside a box for different purposes. Right? Here, what is the purpose? Explaining the rules that we are using, so that the other person can use the same rules instead of trying to use some other rules and getting garbage information. We are telling them what rules we are using so that they can also decrypt it. Right? Remember, we have, for everything, we have different rules. Encryption is a good example. You can have AES, you can have DES, you can have asymmetric, symmetric, thousands of different algorithms. So you have to tell the other person which one I'm using. Okay? Is it clear? Okay. So you have message formatting and encapsulation. You also need to specify what the message size is. Again, why? Because on the wire, it's just 010101. How do you know that this one message has ended and another message is starting if you don't know what the size of one message is? Understand? It's just a big stream of data coming in, 01100010101010. And if you don't know what one message looks like, you cannot cut it and decode it. You have to separate one message from the next message, and for that you need to specify what the size of the message is. Okay? So different protocols are going to use different message sizes. Encoding between hosts must be in an appropriate format for the medium. Right? For example, if you have a wire, you are going to have different sorts of message sizes. For fiber optic, you are going to have different sizes. For wireless, because it's less reliable, you are going to have different algorithms and protocols. So messages are converted to bits. Bits are encoded into a pattern of light, sound, or electrical impulses. It depends on what you're trying to achieve and the medium. The destination must then decode the signals to interpret the message. Right? So you need to specify what the size is. Also message timing, like I told you before, you need to specify how often we are going to transmit a bit. right? The rest is not important over here. We are going to come back to this later on. So let's put like a cross next to it. But essentially, you need to understand how often a bit is going to be sent out, because if you don't specify, then 0 1 and 0 0 0 0 1 1 1 1 look the same, right? So it's the same thing. This is called flow control. How many bits are flowing, and what happens if like there is a glitch in the wire and instead of a 1 you get a 0. All of these things you have to understand as well. Okay. When you are sending out a message, this is the final thing I think over here. So when you are sending out a message, like I said, you can have a receiver, you can have more than one receivers, you can also send it to everybody who's on the network. So these are three basic options. You can send it to one particular receiver, you can send it to everybody who's listening, anybody, right? You start shouting in the middle of the university, right? That is called broadcasting, right? You know what broadcasting is? When you broadcast on the radio, anybody who has a radio can listen to you, right? That is what a broadcast is. So a broadcast is, so this is the broadcast. When you send the message, all the yellow ones receive it, so everybody, right? A unicast is when you send the message, only one receiver gets it. You are trying to send the message only to one particular individual device, okay? And then there is thing called multicast. Multicast is when you send it to more than one, but not everybody, right? So that is a multicast. They have their own purposes. We're going to come back to this. Broadcast is very important for us. Unicast is obvious. You're sending a message to one particular device. So that's obvious. Unicast, nobody actually says unicast because that's normal communication. You send to one particular device. Broadcast is going to be very important for us even in like today's lesson in the next lab. So what is broadcast? You send a message to all the devices which are listening to you, right? Why would you do that? We'll see why, okay? And then there is something called multicast, which is useful in particular cases. We'll come to it when we need it, okay? But you have to understand what's the difference between these three. Is this clear? Okay. Any question?
How we specify the receiver?
We'll come to that. We'll come to that. Right now, we don't know how do I identify this device? I've been saying this. How you can't say this.
Given the IP address?
Yes. So not just that. We have many methods, and we have to come to that. Okay. All right. So what are the protocols? So again, what are the protocols? They are the rules which define communication. How is communication going to take place? And as I told you, we have quite a few different objectives that we need to achieve from this communication, right? Send message from point A to point B. That is just one objective. The message should get there. That is one objective. But that is not the only objective. It should get there securely. That is another objective. It should get there correctly. That is another objective. It should get there, and if somehow it is not getting there, if it did not get there, then I should be informed so that I can resend it. Another objective, right? So all these objectives are there, and for each of the objectives, we are going to have different protocols. So for example, you need to have some sort of a protocol which can define addressing. How do you address the other person? Address is when you want to like talk to somebody, you address them, Mr. Flana and Flana. How are you, and so on and so forth. So you need to be able to address the sender and the receiver. So we have a protocol. We have actually multiple protocols for addressing. You need to have reliability, guaranteed delivery. The delivery should take place. If it doesn't, I should be informed. I should be able to resend it, something like that. So reliability, flow control, efficient rate should be, the data should flow at an efficient rate. It should not be too slow, too fast. If the other device is slow and I have a very fast computer, we should establish a connection speed on which the decoding can also be done. Because remember, the information is flowing on the wire. I'm sending electric pulses. If the other device is so slow that it cannot capture those packets, then packets are going to be lost because the pulse goes there and then it's done. Okay, agreed? So we need to have some sort of an agreement between both parties. At which speed am I going to send the information? Okay. Sequencing. If you have a very large message, I told you each packet is very small, right? So let's say I want to send hello world, and in one packet assume that you can only send H, okay? In the next packet you can send E, and then in the next you can send, how do you spell hello? HELLO, right? So let's say these are 5. So 5 different packets, right? You would imagine that I send out one packet, another packet, another packet, another packet, another packet, and the decoder receives it. The receiver receives it 1, 2, 3, 4, 5, right? But there is a possibility that there are two intermediate devices. One is slow, one is fast. My H goes on the fast one, gets there quickly. E goes on the slow one, gets there slowly. While this is traveling from here to there, the L goes out on the fast one and gets there before the E. So now the packets which are received are H, L, E, L, oh, something like that. So your message is corrupted. So you need to have some sort of a sequencing attached to it as well. You have to say that in this whole message that I am sending you, this H packet is the first one and the E packet is the second one. So that even if they get there out of order over there, the receiver, the decoder can look at H and say 1, okay. L, this is 3, where is 2? And it waits for a while and the E arrives. It says, this is 2. It puts it there and then the L. Understand? This is called sequencing. So you need to have this as well.
So doctor, every message I send it, it's go one character by one?
It's not one character by one character, but each message is broken down. I'm just giving you an example which is easier to visualize, but it is broken down. It's a specific number of bits. Okay? Clear? Okay. Right. So the question for the people who are watching the videos is every message sent character by character? The answer is the character by character is an example to understand. It's sent in a specific length, which we'll see what it is later on. Okay? All right. Error detection. If let's say the H gets there and the E gets there and the L gets there and one L does not get there and the other O, the final O gets there, it's HELO. So the receiver has to have some sort of a mechanism of knowing that there were actually 5 messages, not 4. I got 4. Where is the 5th one? And they will also know this from sequencing because they will have 1, 2, 3 and 5. They'll say, where is the 4? They wait for a while. The 4 doesn't arrive. They send the message back to the receiver, to the sender. Where is the 4th packet? And then we send it again. It's called error detection. Okay? And you also need to have an application interface, which is not very important over here, but eventually at the end you need to have some sort of like a communication with the user. The information has to somehow get to the user. That is not our concern at the moment. Okay? But there are some requirements for this later. All right. So I'll give you an example of different protocols. So these are protocols which you have used, at least definitely used, and you may have seen them a little bit in detail as well. So HTTP, you remember we in Packet Tracer, and if you've done any and used any sort of web at all, in the browser you write http:// google.com or gmail.com or whatever, right? So that HTTP is essentially a protocol. Not essentially, it is a protocol, right? So that HTTP is a protocol. It takes your google.com and it does something with it and encodes it in a format that it can be transmitted onto the wire, right? So I'm being a little inaccurate, I'm not 100% right, but it's a protocol which takes your URL and sends it over the internet, and the information that is brought back, HTML and JavaScript and images and all of that, it interprets the received messages. Okay, so that is one protocol. You have transmission control protocol, which takes care of the transmission. I mean, you specify the senders and the receivers and all of that. So this is going to be like a huge part of our course. So we're not going into the detail of this right now. It's like 2 or 3 different chapters. Right? So it's essentially, it defines what the sender and the receivers are. How do you identify them, right? It's not as simple as it sounds. It has a lot of complications. Not difficult stuff, but it has a lot of material that we have to cover to fully understand this. You also have the internet protocol, which again sounds very similar to them, but they have slightly different purposes. So internet protocol, transmission control protocol, for now just understand that they are used to send messages from one device to another device reliably. Okay, and you have Ethernet. So what is Ethernet? When you connect 2 devices together, like physically, and let's say for the time being, for the sake of discussion, let's say they are very close together. They don't have to be close together, but if they are very close together, they typically want to communicate with each other very quickly, right? For example, if you have a file server over here, right? Let's say we are working with a lab, and I have some starter files which you need for your lab. I put them on this machine. Why? So that you can access them very quickly from this, right? So all the devices which are very close together, we are going to call them local area network. We did this before, right? So we're going to call them local area network. And in the local area network, the addressing or the identification of a sender and receiver is a lot simpler, right? Because there are going to be what, like 20 devices. So these devices use a different protocol which does not have the requirements of this TCP and IP, right? Everybody calls them TCP IP. Nobody calls them transmission control protocol, right? So you have to, from beyond this point, you have to know what TCP means, right? So TCP is transmission control protocol, just the words, right? The concepts are going to be later. So on a local area network, it's much easier to communicate using the Ethernet protocol. Again, kind of wrong, but makes sense, right? So it's a smaller protocol, easier to work with. We are going to come back to this later on, right? Okay. So once you have these protocols, you need to have some sort of a mechanism in which you have, like I said, we have quite a few different protocols. You saw 4 over here. We are going to have, like, in a typical communication, there are dozens of protocol, right? You can think like 27, 28, 30, 35 different protocols which are working to send just one H from one point to another point. Okay, so you need to have some sort of a mechanism to organize them, right? Some sort of like a table which says this guy does this and this does this and this does this and this does this, right? Some sort of way to like formalize them and structure them. So these are called reference models. There are 2 basic reference models. They're not going to make sense if I try to explain them, but they are going to make sense slowly as we look at them in detail, right? So essentially, what we are saying is, we are sending a message from point A to point B. We need different protocols. We need one protocol to make sure that we specify the sender and the receiver, okay? So we need one protocol for this, right? We have to put this in this whole structure. So think of this as a table. This thing over here, this is a table. We have to put it somewhere, right? So at the moment, just look at this. Okay, this is much simpler. So we have to have rules which specify exactly how we identify a sender. Do we give them English names? Device A, device B. As you can imagine, it would be difficult to have this device A, device B, right? It's easy for us humans, but it's going to be difficult because you cannot do mathematics with A and B, right? What if we do numbers? We call this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Might work, right? Turns out it's difficult to work with this as well. We are going to have a specific set of rules which we'll study later on. The point is, in order to identify or uniquely give numbers to senders and receivers, we are going to use a particular protocol. You saw an example of this later on when we did DHCP. It showed us 192.168.0.1, right? That was one example of an address that we can use. Okay. The point is, addresses have rules. You cannot start creating your own like names for machines. You need to follow some rules. So those rules go here. Okay. What happens if you send a message and the message is not delivered properly? You need to have some sort of a rule. So actually, I got it wrong. Sorry. So the addresses are over here, right? What happens if you send out a message and the message does not get there? Then what do we do? Right? There has to be rules for that. Those rules are over here. Right? So the protocols for addressing are here. The protocols for, let's say, error correction are here. Which encryption algorithm are you using? Those protocols are discussed in this portion. Okay? Okay, fine. You have the whole thing encoded. Now you want to send it on the wire. On the wire, when it's going to go, which media is being used? Which medium is being used? Is it wire? Is it fiber optic? What is going to be the speed of transmission? What is going to be the voltage? All of those things. Those are over here. Right? So you have all these different rules which fix in their own little boxes. So everything related to security is going to go over here. So if you are concerned with security, all you have to do is go look at this one box. Do you understand why we have created this structure? If you know what your current concern is, right now I'm trying to figure out if communication occurring between my device and the other device or on my network, is it secure? I don't have to look at these 3 things. Like all the 36 different protocols which are over here, I don't look at them. I only go and look at the application layer. This is called a layer, right? It's called a layer because like in a layered cake, I'm kind of hungry. So in a like think of a cake. So you have one thing, another thing, another thing, another. So you have things which are distinct from each other. Like this is cake and this is like, I don't know, cheese. Why do I have cheese in my cake? So let's say I have cream, and then what else? Like jam, and then you have another layer of cake, right, or something like that. So you have these things which are distinct from each other, right? So similarly, the application protocols are going to be distinct from each other. What happens is when the user starts communicating, the user talks to the graphical user interface. In the graphical user interface, you are going to have some sort of an application, right? Like your browser. The browser is going to take the information from the user and encode it somehow and then encrypt it and then make it in a format that can be sent out. So you take the H, you convert it into its ASCII values, and then you take the ASCII value and then you encrypt it, and then you attach a message right next to it which says that this thing, this garbage of zeros and ones that you see over here, this is an encrypted message which is encrypted using this algorithm. So now you have this one little box. You understand what this is? So now the application layer has prepared its output and it sends it to the transport protocol. And the transport protocol attaches, for example, the sequence number to it. So let's say you have written, hello world, I am trying to send you a message which is very secure. So this is a long message. The transport layer is going to have a protocol which is going to take this whole message, and it doesn't care what the message is. It doesn't care what is being sent. All it knows is that this is a very long message and I need to chop it down into smaller parts, right? And each part is going to be assigned a, now you take this one part and you say, this is part of message ID 259-628-3968. And the messages number. So you're going to be sending quite a few messages. So this is the message number 259, let's say. Let's be reasonable. So 259. And it's the part 1, the first segment. Right? A segment is like a chunk which is cut off. So it's the first segment of this message. And then it takes the second segment and says this is the same message, segment number 2. So that is the responsibility of this transport layer. Okay. Once it is done, then this transport layer hands it over to the internet layer. That is going to associate the sender and the receiver to it. And then it specifies its own information and creates a bigger packet. So you see, you have a little packet, and then you have stuff around it, and then you have stuff around it, and then you have stuff around it. So all of this stuff is being added over here. Eventually, the internet protocol, internet layer is going to hand this over to the network access layer. And that network access layer is eventually going to have some sort of a network interface which is going to transmit this in bits over the network medium. Is this clear? So these are called layers. Right? This is very important. One of the most common job interview questions in all of like computer science is it's going to come from the layers of networks. Right? These are just called networking layers, right? Or layers of the OSI model. We'll see what this means. So this model, which divides all the protocols into 4 different layers: the application layer, the transport layer, the internet layer, and the network access layer. So 4 layers. This is called the TCP/IP model. Remember, these layers aren't anything in themselves. They are just collection. All right, so we're back. So as we were saying, you have quite a few different protocols, and they have been arranged in this particular set of 4 layers, right? So the protocols are still the same. You can arrange them differently, and that will give you the other model, which is the OSI model, right? So what is the difference between TCP/IP model and the OSI model? TCP/IP model basically takes all the protocols that you may need for the communication. It's the same set of protocols. It divides them into 4 parts, 4 layers. Okay. OSI model takes again the same set of protocols, right? All the different protocols, the same protocols, but it divides them into 7 different layers instead of 4, right? So for this application, so we'll see this. So the OSI reference model has these layers, and they start with layer 1, physical, 2, data link. So this numbering is important. You start from the bottom. Okay. Because when people talk in networks, sometimes they say that this is networking layer 4. So you have to understand what layer 4 means, right? You have to remember that layer 4 is transport layer, right? This numbering is important. and it's in this particular numbering for a reason. The physical is very close to the hardware. The application is very close to the user. So information comes from the user, goes to the application layer, which does something to it, which is written over here. This is not important at the moment. We'll come back to this. So application is layer takes care of very high level stuff. Then it hands over the information to the presentation layer, which does something and hands it over to the session layer. So these three combined are essentially the application layer of the TCP IP model, right? So again, I'll come back to this in just a minute. Then you have the transport layer, which is essentially the TCP layer, right? So the transport layer over there. Then you have the network layer, which is the internet layer. Then you have the data link and the physical. These two combined are essentially the network access layer. I am fairly sure that nobody understood what I just said, so I'll show this to you later on. So TCP IP, you have these four layers. So they have this mapping over here. So the application layer of TCP IP model is three layers in the OSI model: the application, the presentation, and the session. So the protocols which are in the application layer here are divided into three further layers over there. Okay, it's going to be the same set of protocols. For example, security is going to be in the session over there. Here it's going to be in this whole big block. Okay, HTTP is going to be in the application layer over there. Here it's going to be again in the application layer. You understand? It's the same set of protocols divided further into 7 and here divided into 4.
So why we have two classes?
Because different people created these, right?
We choose which one.
So generally, the Cisco people, because we are following the Cisco slides, they generally prefer the TCP IP model because, as you can see, it's simpler.
Yes.
Okay, and generally when we're discussing networks, the application layer is not that important for us. We are mostly concerned with the transport and internet layers. Okay, so they have separated these two, and we can deal with them over here, right? OSI is the kind of like the agreed upon model throughout the world. Everybody agrees on it, and that is why we say stuff like layer 3 and layer 4 and layer 5 and layer 6 and layer 7. Okay, sometimes people are just going to say layer 3. They're not even going to say network. They're going to say layer 3. Okay, we actually have devices which are called layer 3 switches, right? They operate at this layer. But the point is, these are two standards. But the good thing is, it doesn't affect us because it's the same set of protocols. Once you understand, we are going to be following this TCP IP model. Generally, in networks courses, the OSI model is followed. So we are going to be following this. But as I said, the application layer we don't concern with anyway. So application session, application presentation and session, that's not our big concern in this course, right? Similarly, the data link and physical layer, they are both in the network access layer, but we only touch upon them in this lesson and probably in one more lesson, and then we're done, right? So the differences are not our concern here. But remember, I'm telling you this again and again, you have to like memorize the layer numbers alongside their names. You have to know that layer 3 is what? Network. I keep forgetting, but you have to remember them, right? Is this okay? All right. So data encapsulation, we've already discussed this. Let's just go over the slide so that you have this. So what this is saying is that when you have a lot of information to transmit in a message, the whole thing cannot be sent together. Why? There are several reasons. One reason you can think of, because it's going over the wire. If there is some fluctuation, you lose the whole message. If there is some corruption, you lose the whole message. If you have smaller parts, you get like 98 parts correctly over there and 2 parts are missing, you can just resend the 2 parts. You don't have to send the whole message again. Make sense? If something goes wrong, you don't have to send the whole 5 kilobytes. You can send just 1 kilobyte, which kind of speeds up the internet. Okay. So, and there are other reasons as well, we'll see as we go along. So this thing is called segmenting the messages. So instead of sending one message in one go, you segment it to increase speed and increase efficiency. Okay. So here's how this happens. If 2 people are sending the messages to this thing, they are going to go over the same wire, right? So there is an intermediate device and then the same wire carries the whole thing. So you need to identify, number one, these 2 are separate messages. Here they are denoted using different colors, but there are no colors on the wire. So you have to somehow assign them numbers. Plus within one message, you need to have a sequence or a numbering system for the different segments. So this thing we don't call address. We call them sequence numbers. Sequence number 1, sequence number 2, sequence number 3. And the sender and receiver have addresses. it's just the terminology, see, the problem with standards is once they define something to be this thing, we have to use their words, because the whole world uses their words, so we have to follow them, and therefore we have to use the correct terminology. Is this clear? Okay, so these are called sequence numbers. Okay, so how does this work? You take one big chunk, one big like message, and you divide it into smaller parts, right? The name of these parts is protocol. Oops. So just a second. So the name of these parts is, did I mess this up? Just a second, okay? Just let me check if I have the thing right. No, I don't. So these things are called protocol data units, right? So data units, parts, data units because they are units, parts of data, and protocol because they are dependent on the protocol which cut down the whole message, right? So initially when you have the whole message, one layer, a protocol on one layer can cut it down into smaller parts and put it in a little chunk, right? So that is going to be the protocol data unit of this protocol, right? So let's see this example. So you have this whole message, email data, which is split into 3 PDUs, protocol data units, right? So when you send it to the next layer, this thing is called a segment. The same PDU, a little box, a little part, that's called a part. Just think of PDU as a part, a box, okay? So this box right now is called a segment, okay? This layer is going to add the transport header over here, which essentially adds the sequencing and all of that information, right? So when you add the sequencing information, you get another box. This thing is also called the PDU, which is a box. But now when you send it to the next layer, this is going to be called a packet. So this is the proper definition of a packet. A packet is a piece of information on which you have added the transport layer header. Okay, so you have added the transport layer header. What does that mean? All the information which is associated with sequencing, that goes into this header box, and now you have a packet, and this packet is going to be now called a frame. A packet. Okay, so once you have this, now you are going to send this from one device to another device, and it is going to go out the network card of one particular device to the network card of the other device, right? So each network card has a unique address. I'll show you the address in the next 2 or 3 slides. But this unique address is now added over here, somewhere over here, right? So over here. Okay. So when it is added, the thing is now called a frame. So PDU, PDU, PDU. You can call all of them PDUs, right? But if you want to give them specific names, they can either be a segment, they can be a frame, or they can be a segment, they can be a packet, or they can be a frame, depending on which layer you are discussing at the moment, which information has been extra added to it. Is this clear? Okay, so let's see another example over here. So this is the same thing over here. These are some examples of which protocols are in the application layer, in the transport layer, in the internet layer, and network access. So these are different protocols. You don't have to memorize the names right now. We'll come back to these protocols, and whichever are important are going to come back, and then we'll discuss them over there, right? This is just giving you examples of the different protocols. So again, these are the most common ones. So for transport layer, you have the transmission control protocol, which is TCP. We saw this earlier. For internet, you have internet protocol. For network access, you have Ethernet, and application, you have HTTP, email, SMTP, all of those things. Again, you don't have to memorize these names, right? We'll come back to these later on. So this is again saying the same thing that we've already discussed, just to completeness. We take the data, we put the information about the TCP protocol associated with it, right? And then we take this box over here and we add the IP information to it, which gives us the further this box over here. This is passed to the next layer's protocol, right? And that adds the Ethernet information, which turns this whole thing into a transmittable frame. And this goes over the wire. So this goes over the wire. The client receives it, and then it starts opening it up. So first it opens up the Ethernet packet, right? So it opens the outer box and see, is this message sent to me? Yes, it is. Okay, fine. I'll go ahead. And then it opens the IP. And then it says, what is the sender? What is the receiver? There is some bit of information over there. Then it looks at the sequence numbers. Is this in the right sequence? Do I have to wait for another message or not? Something like that. And then finally it opens the data and properly decrypts it. Okay. So same thing, You have bigger box prepared coming in, you open the outer box, you see whether it is sent to you, then you open the inner box, and then you take the information out of that, and you keep decoding until you get to the final data. Okay? In an example of an HTTP request, this is going to be finally at the end, you are going to get the HTML web page. Is this clear? Okay, good. So, finally, we come to the actual practical aspect of all of this, where we can actually start discussing stuff. And that is that when you are sending the information from point A to point B, we can have different types of addresses. At the moment, it's not going to make sense why you need different types of addresses. Just give one address, whatever you decide. Like start calling things 1, 2, 3, 4, 5, 6 or whatever, it doesn't matter. But once you have one address, why have another address? Right? So it's going to make sense in just a little while. Probably in the next lesson, but here we are going to introduce the problem of having just one address. But let's start with the very first address, which is very obvious and very straightforward. Is this clear what we're trying to do? This is like the final 2 or 3 slides, okay? So then we're going to stop for today. So let's start with how you can uniquely identify a device, because you have to send message to somebody, you have to uniquely identify them, right? If I'm talking to you, I have to know who you are to communicate with you. Is this clear? So in our machines, we have a network interface card that we discussed last time, right? You have a network interface card which can be wired or wireless. You did this in Packet Tracer. That thing, all of the network devices which are created, whether wireless or wired or whatever, every device is assigned a unique number which is only given to this one device for your computer, this particular computer. That unique address is called a MAC address, MAC address. Okay, or this is given to the network interface card. So this is any device which connects to the internet, to the network, right? So any hardware, all of these hardwares in the world get one unique number. I'll show you what it looks like. And that number is unique to this device only. This will not be given to any other device in the world. Is this clear? This is very important. This is only for this particular device. So if Dell creates 5,000 computers, it's going to have 5,000 different MAC addresses, one for each of the devices. Okay. So even if you buy 2 machines which are exactly the same, they're going to have at least the MAC address different. On the mobile phones, you know this IMEI, right? So IMEI is a number which is very unique for each mobile device, right? Each SIM. So it's kind of similar. All right. So for the devices which are on the same network, right? So same network, same LAN, okay, local area network, same network, you are going to communicate using what is called the MAC address. So the MAC address looks something like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hexadecimal digits. Okay, 12 fours are 48. So 48 bits. Is this clear? Are you all familiar with the binary to hexadecimal conversion? Okay, right. So 12 hexadecimal characters, which means 48 bits in total. Okay, so 48 bits, this is unique across the world, right? So 48 bits, this is unique across the world. Is this clear? Okay, so what you do is you have this address which is assigned to your device over here. So let's say this is A. I'm just going to call this A for ease, and this thing is C. So I'm going to call this C. So when you want to send a message on your local network from A to C in your Ethernet layer over here, right? So over here. So frame header over here, you are going to write sender is A, and receiver is C. Okay, and then you throw it on the wire. Is this clear? So you are connected to a device which is called a switch. So this device is called a switch. I'll explain what a switch is later on, right? It's going to make sense when we do the practical. Right now, I don't want to go into what a switch is. Just think of it as an intermediate device which can connect different things together. Okay? So it's just there in the middle. It's not doing anything, right? So you are going to send a message, and the only wire you have goes to the switch. So you send this in this packet, this frame out on the wire, and you say the sender is what is A, right? So let's just call it. The sender is A. And the receiver, in your message you have written the receiver is C. okay, and you send it out. It goes there. What is the switch going to do? Switch is not C, yes. So the division, the chunking has already been done. You are now looking at one frame which goes out. Right? So you have the whole message, you cut it, you add some information, you add further information, you add further information. At the end, you have one, which is one thing, one box, one piece of information which is very small. This is called a frame. Okay. Now this is going out on the wire. Goes out. Okay. Gets to the switch. The switch looks at it, opens up the Ethernet outside box. It opens it up. Yes. Yes. So it looks at it. The receiver is written as C and the switch is not C. The switch opens it up, says, the packet says, sender is A, receiver is C. Now switch is not C. So the switch knows that this packet is not sent for me. It's sent for C. And because C is also connected to the switch is going to send it out over this wire. Right? How does the switch know that it's this wire and not that wire? We're going to do it in practical. I don't want to do it right now. It's boring if you do it in theory. I'll do the video, okay? And then we'll have this in the video. But the switch is going to send that packet out to the wire which goes to C. When this same packet gets to C, C opens up the box and sees the sender is A and the receiver is C. Right? Sender is A, we call it source and destination. Instead of sender and receiver, we call them source and destination. So the source is A, the destination is C. I am C, yes, I am C. So now it goes and further opens up all the other packets. Is this clear? So the very basic mechanism of communicating on the network is to use the MAC address. Why? Because it's unique. It's hard coded, it's in the hardware, it cannot be changed, it's there. Okay? So if you know the MAC address, which is associated with the interface, you can just use that to send the frames out. Is this clear? Any questions? Right? Okay. So again, what happened? We had the whole big message, we divided it into smaller chunks, and then we added all the extra boxes around it. When the whole box was prepared, which is called a frame, we sent it out over the wire, and on the wire it is going and it reaches the only place that the wire gets to, right? The switch. The switch looks at it and sees that the destination is C, not me. I'm not the destination. I'm not supposed to open the rest of the box. It simply forwards the box to, or the frame, to the wire on which it knows that C exists. So it did not send it to the left wire, it sent it out to the right wire. We'll see how the switch knows, that's later on, but the switch is going to send it over to the C, and when it gets to C, this C, which is FTP server, again opens it up and looks at it and says, okay, this is the frame and the source is A and the destination is C, so I'm C, I'm going to open this up. And then when it opens it up, it says what the rest of the information is, and then it keeps opening it up until it gets to the final message, and then it knows what to do with the message. Okay? So in the case of FTP server, most likely the PC1 is asking for a file. And then it's going to prepare its own frame with the source as C and the destination as, it's sending it back to the PC1. Destination is going to be, source is C. So the server is sending now a response message to the, right? So it's a new message. As far as the network is, yes, it's a response. So you might be right that, yes, I understand that you might be thinking that it's the same kind of conversation. But no. Now when the frame is going out, you say the source is C and the destination is A. It's the responsibility of the application layer to remember that this is a response to the message which I sent earlier on. It's not the responsibility of the network access layer. You understand? You're right, but that's another protocol, not this protocol. This protocol looks at it as a new message. It's a response, is somebody else's responsibility. Okay? Is this clear? That is why we have these layers. That's a good question. That is a good point, but it's not our point. Somebody else has to take care of it. Okay? All right. So this is what goes on. And we have some devices over here. We'll see what that is in a while. Okay. So what is the role of the data link layer? So these are addresses which are called data link layer addresses. Essentially physical addresses. They are typically called physical addresses. Okay. They are used on the same network. It says same IP network, but we don't know what IP is at the moment, so forget about it. It's on the same network. Okay. So these are called MAC addresses. I don't know what MAC stands for. Somebody should look it up and let me know. But everybody calls them just MAC addresses, right? So these are associated, physically embedded onto the network interface card. They do not change, right? They're physically hard coded. Source MAC address will be that of the originator, and the destination will be the destination where you, the recipient, where you want to send this. Okay. So on the same network, we've said that we are going to use MACs. Okay. Now the question is, why don't we just stop here and use MACs of the whole world to communicate? Okay. Do you understand what the question is? Sorry? Yes, so there are a few problems. This is one of those, but let's discuss all of them. So the very first one is, because this is hard coded, if I give this out to anybody in the world, now they know that this address of A belongs to Noman. So later on, if I do something else, they will know, even if I don't give them out my name, they will know that this is Noman communicating with us. So this is a big privacy concern, number one. Okay, because it cannot change. So unless you throw out your laptop and bring in a new laptop, you are known across the world. Everybody knows that it's you doing the communication, which we don't always want. Agreed? Okay, it cannot change. You cannot change it. It's going to be. So that is the first reason. The second reason is, if let's say you have a Gmail server, and the Gmail server is going to have some sort of a MAC address, right? Every device has a MAC address. If you use the MAC address to communicate with the Gmail server, and tomorrow the Gmail people decide to upgrade this server, they throw this out, get another server in, now they have to communicate this to the whole world. Understand? That our MAC address is no longer that one, we sold that, that is bought by Dr. Noman in Ifat University and he's using it. So now everybody is sending me messages. Right? Why? Because they have a list which says google.com is this MAC address. So until they update it, it's a whole big mess. Understand? So big privacy concerns. If you change devices, if you have the device over here and you are sending messages, if I even disconnect from my wired connection and connect to a wireless connection, the MAC address is going to change. Wireless has a different MAC address. The wired card has a different MAC address. So even in the same device, two different networking devices are going to have different MAC addresses. So if you change a device, then you have to do the whole thing again. Is this clear? Right? So, and the third thing is, addresses are based on vendors. So, for example, if you have AAAAAA, the first four hexadecimal numbers are associated with the vendor. So all the Dell devices are going to start with AAAAA, for example, right? So let's say I have a Dell device over here. It starts with AAAAA and then some other number. And then I have, let's say, another vendor. So let's say HP. That is going to be CCDVE, right? So the addresses are created for vendors, not based on locations. So if I have two devices over here, one is from Dell and another from HP and another from ASUS, all their network addresses are going to be completely different. You understand what I'm saying? Because they are physical and each vendor has its own like starting bits, right? So Dell, for example, starts with 10. All the Dell devices start with 10. All the HP devices start with, let's say 11. All the Mac devices starts with 59. Okay, so if two devices are sitting very close together, their MAC addresses are going to be completely different from each other. So it's difficult for us to work with them. What we want to do is come up with a new scheme, which number one is not physically hard coded. So later, if you want to change it, we can easily change it. Agreed? Is this clear? It's not hard coded. It's in software. So if you want to change it, we can change it. Number one. Number two, if we change a device, the new device can be given the same address. For example, I called this guy 259, right? If I throw this out, get a new device, regardless of the MAC address, I can now call this 259. So everybody outside in the world is still communicating with 259. Okay? But that device is now out. Now I'm calling this 259. That is no longer 259. Is this clear? So the second issue is also resolved. Okay? So number one, privacy concerns. I'm no longer sharing my physical address with you. If I say this is 259 today, tomorrow I can say this is 364. So I can change it because it's not physically hard-coded onto the hardware. Okay. Number two, if I change a device, I can use the same address on the new device. So this was 259, I throw it out, I buy a new device, I put it there, and I plug in the same wire over here, and I say this is now going to be 259. Okay. So people are everywhere in the world still recognize 259, they talk still to the 259, and now this is 259. Okay. Is this clear? Okay. Third thing, address is based not on vendors. So this 259, I'm going to say that I am going to give all of these PCs which are in this one lab, I'm going to give them these addresses which I'm making up on my own. I'm going to give them all the addresses starting from 1000. Right? So 1001, 1002, 1003, 1004, 1005, 1006. In the other lab, I'm going to call them 2001, 2002, 2003, 2004. Right? So just by looking at the first digit in the address, I will know which lab they are in. If I want to communicate with the third device on that lab, I can say 2003. Right? It's like that. I don't have to remember anything. Why? Because they are logical. I base them on some logical scheme. Is this clear? Which is particular for my use case. So those things are called, so these MAC addresses are called physical addresses, as the name suggests. They have all of these problems. We solve them by coming up with logical addresses. Okay? Logical addresses. So what are logical addresses? Logical addresses are 32-bit. So the first logical address that we're going to come up with, there are others as well, are going to be 32 bits, not 48 bits. Right? There is a reason for that. And they are going to be in the format. So eight bits here, 8 bits here, 8 bits here, and 8 bits here. Right? So if you have 8 bits, you can go from 0 to 255. Okay? So 1111, 1111, 8 bits. The largest number, if you set all to 1111, 1111, this is 255. You can verify it later on, right? So you can have 1111, 1111 over here, 8 bits. Okay? So combined, they are going to be 32 bits, and we have 4 different blocks here. The reason for that we'll describe later. But 8 bits, 8 bits, 8 bits, 8 bits. Total of 32 bits. Just think of it as a number. Okay? But it's difficult to remember all of this. So we are going to convert them into decimals. Not hexadecimals this time. There is a reason again for that. But this time, not hexadecimals, decimals. Okay? So let's say I have an address 1 dot dot dot. So we are going to put dots in the middle. You'll see again why. Because if you write it in decimals, it's going to be problematic. So let's say we have an address 192. You can convert this into binary. It's going to be some 8 bits. Okay. 16, 0, and 3. 168. 192.168.03. Okay. So these are 32 bits. If you convert them, you can convert them into binary. It's going to turn into 32 bits. Okay. The reason we have dots in the middle is if we don't have dots, it's going to look like 192.168.03. So which is the first block? We don't know. Is it 803 is the first block, or 6803 is the first block, or 3 is the first block? We don't know. So we put dots in the middle. In binary, it's clear. But in decimal, we need the dots to separate 4 blocks. Okay. So now we have a logical address. There is a reason for creating this particular scheme. This is not our point at the. I'm just going to stop here by showing you what the logical address is, and then we are going to work with this. Okay. So now we have a logical address, and this address is called the IP address, because it comes from the internet protocol, right, which does internet routing. Anyway, so we have 4 blocks, total of 32 bits. Each block is 8 bits, and we assign this logical address to each device on the network. Okay. So for example, this is a guy over here. So where is it? So this is a guy over here. We say that it has the physical address of A. We also assign it a logical address, which in this case is 192.168.1.110. Okay, 192.168.1.110. You don't normally pronounce the dots. Sometimes you do, sometimes you don't, but normally you don't, right? So it's 192.168.1.110. Okay, and this guy over here is 192.168.1.9. Okay, is this clear? So now each device on the network has a logical address and a physical address. Okay, the frames are still going to go over the local network using the physical address, but we humans find it much more easy to communicate using logical address because of, where is it, all of these reasons. Okay, we find it easier. So what we're going to do is we're going to assign a logical address to all the devices. This is what the plan for the next lab is, inshallah. Okay, which is going to be Tuesday. Bring your laptops. So we are going to define a network. We're going to give a logical address to all the devices, and then we're going to ask this device, which is 192.168.0.1, to communicate with 192.168.0.3. So we are going to use logical addresses, and somehow they are going to map to the physical addresses, because the network is going to communicate using physical medium. This clear? This is going to be next lab, inshallah. So this is not what we're doing today. This is going to be in the next lab. Any questions? Bismillahirrahmanirrahim. Right, in this lab we are going to set up a basic local area network, and we are going to look at how to do addressing using our MAC addresses. Okay, so that is the basic objective, and we are going to take a look at quite a few different details about the protocol, how it works, and some further functionality of the packet tracer as well. Okay, so let's go ahead and start up our packet tracer. So over here we have the packet tracer, and we are going to place some devices. So the first thing we are going to place is in the end devices, we are going to take a PC and we are going to place it over here. Okay, then we are going to take another PC and place this over here as well. So we are going to connect these two PCs together with each other, and we are going to use a device which is called a switch, right? So for this, go to network devices, and over here you go to switches, which is the second one over here, and just take whichever switch you want. The first one works perfectly fine, so take this one. So this is the 2960 switch. So these are actual devices which you can like purchase as well from Cisco, but we are going to use them over here just for the sake of creating connectivity between devices. Now one very important thing to remember over here is we are going to look at some basic constructs, and it's very important that you follow along with the video and do the initial algorithms, the protocols as we are doing now. Then you can go ahead and explore further later. Okay, so we have these two devices over here, and they are connected to a switch. So what does the switch do? It's going to make a lot more sense when we actually go ahead and use it. Okay, so we are going to add these things over here, and then we are going to add a switch over here, and then you'll understand what the switch does. So let's add another PC over here as well. So PC, or in fact let's go and place another switch which is over here, and then another PC which is going to be connected to this second switch, and another PC which is also going to be connected to this second switch over here. Okay, so now we are going to create our wiring. So first thing, we go to our copper thread through cable and connect the PC, which is fast Ethernet 0, with the switch, which is also fast Ethernet 0 over here. Right, so you are going to connect a fast Ethernet 0 with fast and Ethernet 0/1. So the first fast Ethernet 0 to the switch. Right, so these two are connected. Similarly, straight through cable, PC1, fast Ethernet 0 to switch, fast Ethernet 0 2. Right, so the first one is connected to PC0, and this is going to be connected to this guy over here. Let's take another cable and connect this switch. So click. This time we are not going to take fast Ethernet 0, we are going to take gigabit Ethernet 0. So this is a much faster network card. So this one works at 100 Mbps, and this works at 1 gigabits per second. So we want a faster connection to go between intermediate devices. Typically that's the case. So let's connect this over here and connect it to the gigabit Ethernet 0/1 of this as well. Okay. Similarly, take a cable, PC2, fast Ethernet 0 to fast Ethernet 0/1 of this, and click fast Ethernet 0 to fast Ethernet 0/2 of this. So this is our basic excuse me. So this is our basic local area network connected. So you will notice that there is no internet over here. There is no wireless router. So the last time we created a network, we ask the wireless router to give us the addresses. So we've discussed IP addresses briefly, and now we are going to take a look at how to assign IP addresses. Okay, so there is nobody here who can give us our IP address, so we have to tell ourselves. These are called static IP addresses. So I'm going to PC0 over here. I'm going to click on this, and in the config, I'm going to come over here in fast Ethernet 0 interface. So this is our network card NIC over here. I'm going to give it the IP configuration static, which means this is going to be statically hard coded by me. So this is not going to be given to me by anybody else. Okay, so I'm going to give the IP address 192.168.0.1. So let's call it this 192.168.0.1. Okay, click on this other box and you will immediately see that the subnet mask has automatically been populated as 255.255.255.0. Right now we have not discussed what the subnet mask is. Don't worry about it, just make sure that you write it like this. So IP address we have written, and we are giving this PC0 the IP address of 192.168.0.1. So this is our logical address, and this is our MAC address over here, right? So as you can see, this is our MAC address over here. This is the physical address, right? So physical address which is associated with the NIC, and our logical address is this IP version 4. Think of this as the IP address. This is 192.168.0.1. So this is for PC0. Go ahead and close this. And we cannot see the IP address over here, and sometimes IP addresses are very important. So what we're going to do is add a note over here. So you go over here, this thing, place note, and click, and now you can go ahead and paste your IP address over here and go to, so click on this again to select, click, go to the fast Ethernet 0, take your MAC address as well, copy it, and come over here, double click, and paste this over here. So this we are doing just so we can see the IP address and MAC address while we are working with the simulation. So this note does not do anything, it's just for our ease. Okay, so similarly we are going to click on this select button, go to this PC, go to config, go to fast Ethernet 0, give it another IP address, so 192.168.0. so up until this point this has to be exactly the same. Again, the reason is going to be made clear later on. So it has to be 192.168.0, and here you can give it 2. You cannot give it 1 because 1 is already assigned to PC0. You're going to give it 2, click, and this should work. Okay, let's go ahead and copy this MAC address, close this, place a note here. So this is 192.168.0.2, and the MAC address is this guy over here. Okay, so let's go ahead and click this. All right, so now we have this stuff added over here. The PC is here. Now what we are going to do is we are going to send a message from this PC0 to PC1. So from 192.168.0.1 to 192.168.0.2, and see exactly how the protocol works. Okay, so as you can see, these two are not directly connected. So any information that comes out of this PC0 has to go to this switch, and then it's going to be the responsibility of the switch to somehow get the information to this PC1. Okay, that is what we're seeing in this lab. We are seeing exactly how that is done. Okay, so let's go ahead and save this file. So let's call this packet tracer -lan or basic LAN, whatever you want to call it, and then let's go ahead and save this. Okay, right. So now what we are trying to do is send a message from PC0 to PC1. If we send a message, we can use a command in this PC. So you go to your desktop over here in your command prompt, you can have a command over here which is ping. So what ping is a command which is going to send a very small packet to the target destination. It's going to send it there, and the destination is going to respond with what is called a pong. So it's a ping pong. So you send a message and you get a message back. What this does is it shows you that the messages are successfully going to the other device and you are successfully receiving messages from them. So it is used to establish connectivity, to ensure that connectivity is established. Okay, so we are going to use the ping command. We are going to give it an IP address, so 192.168.0.2. So remember, we are in PC0. Our address is 192.168.0.1, and we are sending a ping message to 192.168.0.2, which is PC1 over here. Okay, we are not using the MAC address. We are going to use the IP address because typically we work with logical addresses, but they are going to be translated to MAC addresses, which we'll see in just a minute. Do not hit enter at the moment right now. If you hit enter, it's going to like mess things up, right? So don't hit enter. Just wait. Ping 192.168.0.2 and then wait. Move this to a side. Come to this main screen over here and you will see that there are two buttons over here, real time and simulation. So what real time does is when you do any command, it happens instantaneously. What we want to do is run a simulation which performs one action and then stops the simulation so that you can explore what's going on, right? So it's easier to demonstrate this. So let's go ahead and click on simulation and you will see this thing pop up over here. Let's go back to our ping command. So that is, so PC0, this guy over here. Now I'm going to hit the enter. So if I hit enter, you will see a couple of things happen. So take note of what happens over here and what happens over here. Okay, so I'm going to hit enter. So see, a message has been prepared. So this is an envelope. A message has been prepared. We're going to see what this message does. Okay, so if you see here, if you click on this envelope, you will see a lot of material over here. So these are your OSI model layers, which we have seen in class. So starting from layer 1, 2, 3, 4, 5, 6, and 7. So in layer 1, this is the physical layer. So nothing fancy going on over here. This over here is the data link layer, which has the information about the addresses. So this has a lot of very, very useful information over here, right? So let's go ahead and take a look at this. So forget about this thing. So this is layer 2 because we are in layer 2. This is an Ethernet header, right? So Ethernet is the layer 2 protocol, which allows us to do communication on our local area network. That is the Ethernet protocol, okay? Come over here, source IP is 192.168.0.1. That is where our source is, this PC over here. Destination is 192.168.0.2, which is where we want the packet to go. Right now it's sitting here. So our simulation mode has basically stopped our packet right here. It's still there. Nothing is going on over here. Okay. So everything is now stopped in time and we are exploring it. All right. So in header, in our layer 2 header, we have 0010.117d D2D2, which is the MAC address over here. So this is the source MAC address and the destination MAC address is FFFF, FFFF, FFFF. Why is that? We want to send a message to PC1 and the MAC address is 00016476AB2E. So shouldn't that have been in the destination over here? Yes, but the problem is when we initiated the packet the first time, we have never communicated with PC1 before. So the first time you initiate a packet, you don't know what the MAC address is. You are given the IP address by the user. I just typed it myself, but we don't know who this IP address is assigned to. So we have to figure it out somehow. And that is where the Ethernet protocol comes in. Okay, so what we are going to do now is we are going to send this packet out to everybody. So that is what this FFFFFFFFF means. So this is a broadcast packet. What does a broadcast packet means? Remember from theory, a broadcast is you're sending a message out to everybody who would listen to you, like everybody, right? So what this means, if you put the destination MAC address as FFFFFFFF, so all ones, right? All 48 bits once. If you put that in your destination address, that turns it into a broadcast packet. What that means is this packet is going to be sent to everybody on the network, on the local area network. It's going to be sent to everybody. Right now that everybody is just this switch. Okay, you are only connected to one switch. So it's going to be sent to this switch over here. Okay, is this clear? If you come over here, you can actually see the PDU which is going to be sent out. So this thing is over here. As you can see, it has quite a lot of material here. So you have starting from bit 0, all of these are pieces of information such as the preamble, destination address is over here that you can understand. This is essentially the thing which is flowing over the wire. Okay, and as you can see, these are all the different pieces of information over here. Source MAC address, target MAC address is broadcast. It says 0000. It's supposed to be all Fs. We have target IP address, which is this guy, source IP address. So all this information is encoded in this PDU, right? So this is the packet which has been established. So think of this as starting from bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, all the way up to bit 8, and then going forward. So this should be one long line, but because that would be difficult to read, they have broken it down into different rows. So think of this as one very long line going all the way to the right of the screen and like outside as well. So these are going to be the whole thing. Okay, so this is your PDU. Anyway, coming back to this thing over here, the PDU is not important. So OSI model over here. So we have all of this information here, And in this we have, so let's reduce this so that we can see it properly. So this is the source and this is the destination, which is the FFFF. Okay, so let's go ahead and close this. What we're going to do is we're going to click on this next step, and that is going to move the simulation one step further. Okay, capture and then forward. So we click, and now you can see that the packet has gone to the switch. So the packet has reached the switch. If you click on the packet, you will see that in layers, the information that we received was the same thing over here. And now out layers is the stuff that this packet is going to do in the future, right? So see what this is going to do. It's going to send this out to fast Ethernet 0/2, which is this thing over here, if you remember. So this was fast Ethernet 0.1 and this was fast Ethernet 0.2. It's going to send it out on this wire and on this wire. Okay, so see, gigabit Ethernet 0.1, which was this gigabit Ethernet, and this was fast Ethernet. So what a switch does, a switch is a device which operates on layer 2. Okay, what it does is it looks at the incoming packets and forwards them. That's it. What is it doing for this particular packet? It sees the packet, it sees that the destination address is FFFFF, so a broadcast address. And what a switch does for a broadcast address is it forwards it out to all the interfaces that it is connected to, except the one from which the packet came in. I'll say this again. For a broadcast packet, a switch forwards it to all the outgoing ports. So it has 3 ports, 1, 2, and 3. It's going to forward this packet to everybody except where it came from. So these are the 2 things where it's going to forward the packet. Okay, so it's going to forward this over here and this over here. Okay, what is that? The reason for that is now switch is forwarding your packet. So you only had to send 1 packet, and now it's going to send it, forward it out to all the people who are connected. So if I had 10 PCs connected over here, all 10 would be forwarded this one message by the switch. Okay, we'll see what the use of that is in just a minute. Okay, so that is it. So you can go ahead and close this. You can click on this message over here, or you can click on this PC0 over here, and that is going to show you the same thing. Okay, so let's go ahead and see the next step. So we sent the message to the switch. The switch is now going to forward it to all the interfaces except where the packet came from. Why? Because this is a broadcast packet. So click and see, copies have been sent to PC1 and to switch 1 over here. Okay, now the switch 1 is going to open this up, and it's going to see what? So this is the source. So this is the source, this is the destination. What is this switch going to do? It's going to do everything that the switch does. What is that? Forward it to all the interfaces except where it came from. So what are these? Fast Ethernet 0.1, this guy over here. Fast Ethernet 0.2, this guy over here. Okay, so it's going to forward this switch 1 is going to forward to these 2, and this switch has already forwarded this message over here. Okay, so your packet, your message is essentially going to reach everybody, which is what the broadcast is. Okay, let's go ahead and close this. Go over here and take a look at this. What is this? This says this is the information which has come in. So 0010 is the source and the destination is FFFFFF, but it also has this information over here. Destination IP is 192.168.0.2, and this PC knows that I am 192.168.0.2. So what is it going to do? It's going to say that now I am going to inform the switch, right? So it's not going to inform the switch, but it's going to accept the packet. These 2 PCs, when they receive the packet, they are going to reject them. Why? Because they are not the destinations and they are also not switches, so they are not going to forward it anywhere. So each device can either forward in case it's an intermediate device, or it can accept the packet if it is the intended recipient, or it can reject it. So this guy over here is the intended recipient, so it's going to accept the packet, and these 2 are going to reject the packets. They're not meant for us, we don't care. Okay, so let's go ahead and run this one step further. So see, this basically tells the switch that yes, it has been received. So this is a response. So we'll see this in just a minute. And these 2, see little crosses over here, they have essentially rejected the packets. They're not meant for us, we can forward them, we're done. Okay, so this response has now gone over here. If you click on this, you will see that now the source is 0016476 AB2E, which is this guy, and it's sending a message to this guy over here. Okay, and the protocol over here is ARP. We'll see what ARP is in just a minute. Okay, so this is essentially telling it that now the packet has been received. Okay, and the important thing to notice over here is the destination address is no longer FFFFFF. So it's not a broadcast packet, it's a packet addressed to a particular place. Okay, where is this particular place? This is this PC0 over here, D2D2, right? So the switch is now, because it's not a broadcast packet, the switch is not going to send it out to everybody. It's going to send it out to a particular address, particular interface. The interface which it knows has this address. How does the switch know which port has this address? So remember the first time the packet was sent to this switch over here, right? So when the packet was sent to the switch and it forwarded it, the switch is going to keep one piece of information with it. When the packet came from over here, right? So let's go back if we can. So when the packet came from over here, the switch saw that the sender was 0010.117D D2D2 and it came in on this port. So the switch is going to keep this information with it. Okay, so if you click on the switch, if you go to CLI over here, right, so let's move this out. Over here, you can have the configuration CLI command line interface for the switch. Here you can say, you can issue a command and it will show you the information it has about these addresses, right? So we are going to say over here, show MAC, and you can hit question mark and it will show you what it can do, right? So you can say question mark and it will show you all the commands. So you say show question mark, it will tell you all the things you can tell show. So show MAC, the actual command is show MAC address dash table. Okay, so what this is going to do is it's going to show you the address table which it has maintained. So if you hit enter, you will see that it has noted that 0010.117D, so 0011.117D D2D2 is attached to my fast Ethernet 0x1. Okay, so this guy over here is attached to fast Ethernet 0x1. And because we have received a packet from here as well, it knows that my 0001.6476 A2B AB2E is attached on my FA to 0x2. So this is fast Ethernet 0x1, this is fast Ethernet 0x2. You just have to keep track of these things in order to fully understand them, right? So it's very important that you note all the information. We should probably go ahead and put a note. So over here, so this is fast Ethernet 0x1. So this guy is fast Ethernet 0x1 and click, this is fast A 0x2 and this thing over here is gigabit Ethernet 0x1. So 0x1. Okay, let's move these around so that they are clearer, and let's go and look at our switch. So see, this thing is attached to this port, this thing is attached to this port. So now when this packet comes along, right, so this thing over here, so let's move this out, and in this packet it is written, so in this packet it is written that it's supposed to go to this guy over here. It's written that it's supposed to go to 0010.117 D2D2. It knows that it should forward the packet on this port only. Okay, and that is what is going to happen. Take a note of the envelope, this guy over here, it's going to go over here. See, only that one place, right? So this is how the whole thing works. You give it the IP address, you don't know where the MAC address is, you broadcast it. The switch is going to broadcast it further to all the ports except the sender. Anybody who is not the intended recipient is going to discard it. If there are other switches, they are also going to forward it. You are going to discard if it is not meant for you. If it is meant for you, you are going to send back a response. While the switch is forwarding all of this stuff, it's always going to look at the source, and because it knows which port the packet is coming in, it's going to take a note of it with itself, noting that MAC address this is attached on this interface, MAC address this is attached on this interface, and so on and so forth. Okay, so let's take this a step further. So on this PC0, we are going to see there is no output over here at the moment. So if you go ahead and click on play, it's going to actually start doing all of these informations, right? So all the forwarding, it's going to go ahead and do it. Okay, so in the meanwhile, if you go to PC0, this thing is happening in the background, and you will see that when we get the message back, we are going to see a ping response over here. Okay, so as soon as the packet gets here, we get a response over here which took this much time, and so on and so forth. So reply from 192.168.0.2 bytes is equal to 32 bytes were received It took 8 milliseconds, and forget about the TTL for the moment. Okay, so we got the response, we sent another message, it goes over there, we get the response back, and see if it's going to go back over here. We get the second response, and we're going to send a third one out, and for that let's stop. Okay, so we got this over here, see all the log over here. So let's try to do another one. So we are going to start another message. So that switch is doing something else, right? So that is not related to us, so forget about this. This is some just regular interval updates going on in switches. We are not concerned with these. Let's take a look at this packet over here, right? So this packet which has been sent. So see, now we are no longer broadcasting. We are sending it from our source to a particular address, A to B, A, B to E, right? So we are no longer broadcasting over here. So once the broadcast is done and the address tables, MAC address tables have been prepared, then you can go ahead and just use the source and destination directly. So here's what the switch does once more. If the packet is broadcast, it forwards it to all the interfaces except where it came from. If it is a targeted address, not broadcast, unicast, then it looks at its address table, right? So it looks at its address table, which is this guy over here. It looks at the MAC address, right? And then it is going to forward it to all the to the particular interface where it's supposed to. Okay, if it does not have the address in the MAC table, it's still going to do a broadcast. Okay, so let's go ahead and close this. So this thing over here, let's go ahead and play this until the whole thing is done, and then I'm going to show you that a similar table is prepared over here in the PC as well, right? So let's go ahead and close this and say ARP, which is the protocol which is taking all of these things, and let's say -A, right? So this is saying that we remember, because we got the message response, we remember that 192.168.0.2 has this physical address. So the table which has all of this is called the ARP table or the address table, and the ARP stands for Address Resolution Protocol. It's taking the address, which is the logical address, and it's resolving it or translating it into the physical address. Therefore, this is called the Address Resolution Protocol, or it takes the IP address and translates it to the physical address, because eventually in the local network, the MAC addresses are what are used for the communication. Okay, hopefully this is clear. Let's go ahead and close this. So I'll say this again. We used Ethernet to sending local area network packets. So let's go to real time. If you want to send a packet out, you need to know the IP address. Okay, you need to know the IP address. There are methods of resolving IP addresses as well. We'll come to those later, but for now, you need to know the IP address. You don't have to know the MAC address. If you know the IP address, you send out a broadcast which goes to everybody on the internet, on the network, on the local area network. If it gets to a switch, the switch forwards it to everybody except the port where it came in from. If it gets to a end device, which is not the intended recipient, then it is dropped by them. If it gets to a device which is the intended recipient, they respond to it. The switch, in the meanwhile, whenever a packet comes in, it maintains a table which says this MAC address is on this port, so that it can later forward it explicitly to the port which is needed. If you have a particular device's MAC address in your packet and you send it to a switch, the switch is going to look up the MAC address on its table, address table, and forward it only on that port. Okay, so hopefully this is clear. Let's go ahead and click on this PC2 and give it an IP address as well. So let's call this 192.168.0. So up until this point, they have to be the same. For the same network, they have to be the same. And then let's call it 101, just to separate it from everybody else. Okay, so sorry, I made the configuration on the wrong place. This has to be fast Ethernet 0 IP address over here, and then click on this. Go ahead and copy the MAC address because we want to put it in a note. So 192.168.0.101. So let's go ahead and add a note over here. So 192.168.0.101, and the MAC address is this guy over here. We're almost done. So let's go to this PC over here. Go to the command prompt. We don't have this 192.168.0.1 in our address table. So what's going to happen? Let's go to simulation. Let's go to our PC0 and let's say ping 192.168.0.101. this time. Okay, so hit enter. A packet is going to go out as before. This is going to be a broadcast packet. Why? Because we don't know what 192.168.0.101 looks like. Right? What's the MAC address? We don't know. So we're going to send out a broadcast packet. Click on this, verify that this is indeed a broadcast packet. Click on next, goes to the switch. Because it's a broadcast packet, the switch is going to forward it to all the devices. Okay. Now switch 1 looks at it. Again, it's a broadcast packet. Switch 2 is going to send it out to all the locations. Okay. So that guy over here simply discarded it because it was not intended for it. That's done. Similarly, this guy responds, this guy rejected it. This is the address, so it sends it back. The switch, this switch over here, if you click on this and you say in CLI, if you say show MAC address dash table, it knows that 000 CA911C, this is gigabit 01. So this is this address switch over here. 00101170 D2D2, which is this guy over here. This switch knows that it's attached to its giga 0 by 1, which is this guy over here. Okay, so this is giga 01 of this, and this is giga 01 of this. Right? So very important to note, this switch 1 does not know how far this PC0 is, how far this 00101170 D2D2 is. It doesn't care. All it knows is that if I have to send a packet to this guy, I send it over on this wire, gig 01. So once this goes out on gig 01, it's going to be the responsibility of this guy. So I no longer care. I, switch 1, no longer care what happens to this packet. All I have to do is send it over here. And this is a very powerful concept in networks. All you worry about are the devices which are connected to you. You come up with protocols which basically help you decide based on who you're connected to. You don't have to worry about the rest of the internet. And that is what makes things really work very easily. Okay, so let's go ahead and close this. And because it's going to send it out over here, that's all it cares. So the packet gets here. Okay, now this switch, when it looks at the same thing, right? What's the address? D2D2. This knows that D2D2 is attached over here. So it's the responsibility of switch 0 to actually get the device over here. It was the responsibility of switch 1 to send it to switch 0. And now it's the responsibility of switch 0 to send it to the proper location. How does switch 0 know where to send it? Again, you go to the, you click on the switch, you go to the config, you say show MAC address table, just for the sake. So again, it knows that 0, so D2D2 is on FA0 by 1, so it's going to send it over here. It also now knows that 0050, 0F8, 5334. So 5334, if I want to send a message to 5334, I send it out on this wire. Right? So see, all of these pieces, little pieces combined together, are working very, very efficiently now. Okay, so send the message out, and the message has now reached. And now, because we know what the recipient is and we know the whole route, we can send a ping message. So ping message goes out, goes to switch 1, not broadcasted. Switch 1 sends it to the particular interface. The particular interface sends it back to switch 1, which sends it to switch 0, and you get the response back to PC0. Again, so this is extra pieces of information. Forget about this. PC0 sends out the message, which has a particular MAC address at the target. How does it know? Because it has its own ARP table, address resolution protocol table. Switch 0 forwards it to switch 1, which forwards it to PC2, and so on and so forth. Okay. Make sure that you run this a couple of times and make sure that you look at the packets as well and understand what's going on over here. This is really, really important, right? So we are only looking at these two first layers at the moment. Later on, we are going to come back to layer 3 and layer 4 as well.